For the past few years, the James Webb Space Telescope has dazzled us with visions of the universe that look like they've been painted by a cosmic artist. Clouds of dust sculpted into pillars, newborn stars glowing like lanterns, galaxies colliding in delicate swirls. These images have redefined our idea of what space looks like. They're not just pictures, they're windows to the very beginning of time, floating far beyond Earth's atmosphere. Webb is unbothered by weather, pollution, or turbulence. From its silent perch a million miles away, it shows us the cosmos in its raw, unfiltered beauty. But here's the question that few people dare to ask. What if we could do something like this from Earth? Imagine a telescope so powerful, so precise, that it could rival the clarity of space telescopes like Hubble and Webb without ever leaving the ground. A telescope capable not just of snapshots, but of movies, tracking the night sky as it shifts, capturing every transient burst, every new supernova, every hidden asteroid in real time. That future isn't coming, it's already here. This is the Vera C. Rubin Observatory. Built high in Chile's Atacama desert, one of the driest, darkest places on Earth, it represents the boldest attempt humanity has ever made to map the sky, not as a static canvas, but as a living, breathing story unfolding before our eyes. Unlike Webb, Rubin isn't about peering deeper into one tiny patch of the universe. Its mission is far more ambitious. Every 3 nights, it will scan the entire southern sky, creating a panoramic time-lapse of half the heavens. Over a decade, it will build the most detailed map of the universe ever attempted, not just in space, but in time. Think of it this way: while Webb gives us masterpieces worthy of a museum wall, Rubin is making the biggest home video of the cosmos ever recorded. Every star, every galaxy, every comet and asteroid catalogued, tracked, watched as they move and change. Where Webb reveals astonishing detail in narrow slices of sky, Rubin captures the grand stage. Its images stretch across areas so wide they'd cover 45 full moons in one shot. Imagine standing on a hill and seeing not just one tree in detail, but the entire forest. The valleys, the rivers, the wildlife, all in motion together. That's what Rubin gives us. And with its revolutionary camera, the largest ever built, each image packs more data than your brain can truly comprehend. A staggering 3.2 billion pixels. To display a single Rubin image, you'd need nearly 400 4K televisions tiled together. This isn't just about seeing the sky, it's about recording it. Every night, Rubin will collect 20 terabytes of data, enough to fill 1,000 iPhones daily. A dedicated 100 gigabit internet pipeline will beam this fire hose of cosmic information from Chile to data centers in the United States. Astronomers worldwide will tap into it, sifting through the sky like a searchable video library, and it won't be hidden behind closed doors. Rubin's data will be open, available not just to elite scientists, but to students, researchers, even curious amateurs around the globe. The universe itself democratized. But what makes this story even more powerful is the name engraved on the observatory's walls: Vera C. Rubin. A woman who, in the 1960s, stood in observatories where few women were welcome. A scientist who noticed galaxies spinning faster than their visible mass should allow. A mother balancing 4 children and a career, who became the first astronomer to deliver compelling evidence of something unseen, something we now call dark matter. Her discovery revealed that the universe we thought we knew was only a fraction of the truth, that most of reality, 85% of matter, is hidden, invisible, waiting to be found. And now the telescope bearing her name is built to do exactly that: uncover the invisible, track the hidden, and reveal the changing universe on a scale we've never imagined. This is not just another telescope, this is a cosmic time machine designed to capture the universe in motion, to find the asteroids that threaten our planet, to catch exploding stars in the act, to trace the faint fingerprints of dark matter and dark energy across billions of galaxies, to turn the sky itself into an unfolding movie, one that humanity will watch together. So as breathtaking as Webb's portraits are, Rubin offers something different, something equally extraordinary: Because if Webb shows us where we came from, Rubin will show us where we're going. Welcome to the beginning of a new chapter in astronomy. Welcome to the Vera C. Rubin Observatory, a telescope like no other. In the 20th century, astronomy was dominated by men. Observatories, conferences, and research institutes rarely welcomed women. Into that world stepped Vera Cooper Rubin, a quiet, determined scientist who would change our understanding of the universe. Vera was born in 1928 in Philadelphia. As a child, she would stare out of her bedroom window for hours, watching the stars drift across the night sky. At just 14, with help from her father, she built her first telescope from spare parts. While other kids dreamed of becoming teachers or doctors, Vera already knew she wanted to be an astronomer. But society had other ideas. When she told teachers about her dream, they discouraged her. Science isn't a career for women, they said. One guidance counselor even suggested she should be an artist instead, because girls don't go into physics. But Vera didn't listen. She enrolled at Vassar College in New York, where Maria Mitchell, America's first professional female astronomer, had once taught. Vera graduated in 1948 as the only astronomy major in her class. From there, she went to Cornell University for graduate studies, where she studied under great minds like Richard Feynman and Hans Bethe. Even then, her research was bold. Her master's thesis suggested galaxies weren't evenly spread across space, but clumped into clusters and superclusters. Radical thinking at the time, and not everyone was ready to hear it. By the early 1960s, Vera was raising 4 children with her husband Robert. She balanced family life with a demanding research career, something her male peers rarely had to consider. On some nights, she even brought her kids along to the observatory, tucking them into sleeping bags while she gathered data. It was in this period that she began the work that defined her career. At the time, astronomers believed galaxies rotated like the solar system. Stars closer to the center would move quickly. Stars further out would move slowly, just as Neptune takes 165 years to orbit the Sun, while Mercury takes only 88 days. The math seemed simple, but Vera wasn't convinced. Working with instrument maker Kent Ford, she began measuring the rotation curves of spiral galaxies. Using a spectrograph, they tracked the motion of stars and gas, carefully charting their speed at different distances from the galactic center. The results were shocking. Stars on the edges weren't slowing down. They were moving just as fast as the stars near the core. According to the laws of physics, that was impossible unless something invisible was adding extra mass. That something became known as dark matter. The idea wasn't completely new. In the 1930s, Swiss astronomer Fritz Zwicky had noticed strange motions in galaxy clusters. He suggested there might be hidden matter, which he called dunkle materie, dark matter, but his claims were ignored. Rubin's evidence was different. Her data was precise, repeatable, and impossible to dismiss. She showed, galaxy after galaxy, that the pattern was the same. The universe contained more matter than we could see. The implications were staggering. Stars, planets, gas, dust, everything visible accounted for less than 20% of the universe's mass. The rest was hidden, mysterious, invisible. Rubin had uncovered proof that most of the universe was made of dark matter. At first, many resisted her conclusions. Some questioned her methods, others doubted her interpretation, and of course, being a woman in science made her an easier target for skepticism. She once recalled attending a conference where a male colleague joked, "You're here to keep the wives company, aren't you?" But Vera didn't fight with anger. She fought with evidence. She measured more galaxies, she collected more data, she presented her results again and again. The numbers always told the same story, and slowly the community came around. By the late 1970s, her work was widely recognized as the most compelling evidence yet for the existence of dark matter. Still, Rubin's story wasn't just about discovery, it was also about resilience. She worked in an era when women weren't welcome in the halls of science. At one observatory, the only bathroom had no sign for women, so Rubin simply made one herself and taped it to the door. she refused to let exclusion stop her. Beyond her research, she became a mentor to younger women in astronomy. She encouraged them to pursue science, to publish boldly, and not to give up when doors closed. She often said, "There is no problem in science that can be solved by a man that cannot be solved by a woman." Over the years, Rubin received many honors. She was elected to the National Academy of Sciences. She received the Gold Medal of the Royal Astronomical Society, only the second woman to do so since Caroline Herschel in the 1800s. But one award always eluded her, the Nobel Prize. Many believe that omission remains one of the greatest oversights in science. And yet, her true legacy is not a medal or a title. It is the transformation of our understanding of the cosmos. Thanks to Rubin, we now know that the visible universe is just a small fraction of what exists. The vast majority lies hidden, waiting to be revealed. That's why the telescope carrying her name is so meaningful. It's not just an honor, it's a continuation of her mission. Vera Rubin spent her life uncovering the invisible. Now the observatory named after her is built to do exactly the same. Rubin passed away in 2016 before the observatory was completed, but her influence continues. Every time astronomers talk about dark matter, they're building on her work. Every young woman who enters astronomy today walks a path she helped to clear, and every image captured by the observatory that bears her name is part of the story she began. Her life proves that science is not just about data, it's about courage, it's about persistence, it's about daring to see what others cannot. Vera Rubin saw the invisible, and she left us the tools to keep searching. High in the Chilean Andes, there's a place where the sky almost never sleeps, a place where the air is so dry and the nights are so consistently clear that astronomers from around the world have built their most powerful observatories there. This is the Atacama Desert, one of the driest places on Earth, a landscape so barren some parts haven't seen rain in centuries. But for astronomy, it's paradise. Sarapajon, the mountain where the Vera C Rubin Observatory stands, offers over 300 clear nights each year. That means scientists don't have to wait weeks for cloud cover to pass. They can observe night after night, gathering data with almost no interruptions. The atmosphere here is thin, calm, and remarkably stable. There's minimal turbulence to distort the view of distant stars, and with virtually no light pollution, the night sky blazes with stars brighter than anywhere near cities. For ground-based astronomy, this is as close to perfection as it gets. It's no accident that Rubin is surrounded by some of the biggest names in modern astronomy. Just a short distance away stands the Gemini South Observatory. Nearby, the giant Magellan telescope is rising, destined to be one of the most powerful optical instruments ever built. And not far off, the European Southern Observatory's extremely large telescope is taking shape, with a mirror nearly 40 meters wide. This region has become the beating heart of global astronomy, a cluster of observatories, each contributing its own unique perspective on the universe. So why is Rubin special? Because while space telescopes like Hubble and Webb escape Earth's atmosphere entirely, Rubin has something they don't: scale. It doesn't just take narrow snapshots, it surveys the whole sky. From this desert mountaintop, Rubin will scan the heavens again and again, building a dynamic movie of the cosmos. Without Chile's unmatched skies, that mission would be impossible. But location is only half the story. The other half is Rubin's digital eye, the largest camera ever built for astronomy. And when we say large, we mean enormous. This is a camera the size of a small car. It weighs nearly 2,800 kilograms, heavier than an SUV. And yet, it is precise down to the tiniest photon of light. At its heart are 199 individual sensors. Together, they produce images at a resolution of 3.2 billion pixels. Let that number sink in. 1 billion pixels alone would overwhelm most computer screens. 3.2 billion is beyond what the human eye can take in at once. If you wanted to display just one Rubin image, you'd need to tile together 385 4K televisions. That's how much detail is captured in a single shot. And Rubin doesn't just take one photo. Every night, it captures thousands. Altogether, that's 20 terabytes of data every single night, enough to fill about 1,000 modern smartphones every 24 hours. In just 1 week, the Rubin Observatory generates more data than some observatories collect in a year. Over its 10-year survey, it will produce tens of petabytes of data, a treasure trove for astronomers around the world. But moving that much information is no small task. The observatory is in Chile. The data centers that process it are in the United States. How do you move 20 terabytes a night across continents? With a dedicated, high-speed internet pipeline. A 100 gigabit per second connection beams the data from the Andes to Miami, Florida. From there, it flows into a network of research institutions ready for analysis. The system is so fast, it can transmit Rubin's nightly haul across the globe before the next evening's observations even begin. This is why the LSST camera is more than just a machine. It's the digital eye of humanity. It sees what no human eye can. It records the faintest galaxies, the fastest moving asteroids, the briefest flashes of exploding stars. It turns the night sky into data that can be shared, searched, studied, and compared. Data that doesn't belong to one scientist or one nation, but to all of us. When you put it all together, the pristine skies of Chile, the stability of Cerro Pachón, the world's largest digital camera, and the massive data pipeline, you get something extraordinary. A telescope that rivals the clarity of space observatories, but with the scale and power only Earth can provide. From one of the harshest deserts on the planet, humanity is building a new vision of the universe, and it all starts with the perfect place and the perfect eye. At the heart of the Vera C Rubin Observatory sits a machine unlike any other, the Simoni Survey Telescope, a giant built for one purpose: to capture the night sky in extraordinary detail, to do it over and over again. The primary mirror stretches 8.4 meters across. That alone would make it one of the largest telescope mirrors in the world. But Rubin doesn't stop there. Above it sits a secondary mirror 3.5 meters wide, and behind the primary, a third mirror 5 meters in diameter. Together, they form a 3-mirror system. Most telescopes use just 2 mirrors, a primary to gather light and a secondary to focus it. But Rubin's design is different. The addition of the third mirror corrects distortions that usually creep in at the edges of an image. It flattens the field of view, sharpens the detail, and allows the telescope to capture wide swaths of the sky with incredible clarity. This design, called a 3-mirror anastigmat, is rare and technically demanding, but it's what gives Rubin the ability to see sharply across areas of sky so wide they would blur in other telescopes. To put it in perspective, Rubin's field of view is so wide, a single exposure can capture an area equal to 45 full moons, and every part of that image is crisp. No distortions at the edges, no smudging, just millions upon millions of stars and galaxies, each as sharp as if you were staring at them through a magnifying glass. With its 8.4-meter primary, Rubin ranks as the 7th largest optical telescope in the world. But size alone isn't what makes it special. What makes it unique is its combination of size and speed. Where Hubble and Webb focus deeply on tiny regions of space, Rubin was designed to look wide and fast. Instead of peering for weeks into one galaxy cluster, it sweeps across half the sky in just 3 nights. It's less of a microscope and more of a cosmic scanner. This brings us to its mission. The Legacy Survey of Space and Time, or LSST, a decade-long project to map the universe not as a still picture, but as a movie. Every 3 nights, Rubin scans the entire southern sky visible from Chile. It repeats this cycle again and again, layering image upon image, year after year. The result is not just coverage of space, but coverage of time. Think of it like this: the Sloan Digital Sky Survey, one of the greatest astronomy projects of the last century, took 20 years to map about 35% of the sky. Rubin can achieve something similar in just 3 days. That's the difference in scale. It compresses decades of work into a matter of nights. Over 10 years, the LSST will map 18,000 square degrees of sky, essentially the entire southern hemisphere. It will repeat this map thousands of times, tracking how the cosmos changes, stars that brighten and fade, asteroids that drift through, supernovae exploding in distant galaxies, even the slow tug of dark matter bending the fabric of the universe itself. This is why scientists call it a time-lapse of the universe. Each frame is a moment in cosmic history. Put them together and you watch the sky come alive. For the first time, we won't just see a frozen image of the universe, we'll see it breathe, and the scale of discovery is staggering. The LSST is expected to catalogue millions of new asteroids and comets in our own solar system. It will capture thousands of supernovae, catching many within days or even hours of their explosion. It will map billions of stars in the Milky Way, refining our picture of our own galaxy structure. And it will detect the subtle patterns of dark matter and dark energy shaping the expansion of the cosmos. This is more than just a telescope. It's an engine of discovery, a machine designed to answer some of the biggest questions in science. What is the universe made of? How is it changing? And what surprises are still out there, waiting to be found? When you combine the sharpness of its three-mirror system with the relentless sweep of the LSST survey, you get something revolutionary. A telescope that doesn't just take pictures. It creates a living record of the universe, not just space, but time. In the next decade, the Simony Survey telescope will generate a cosmic archive unlike anything we've ever had. One that future generations of scientists will study long after the last exposures are taken. And one that might just hold answers to mysteries we can't even imagine yet. In June 2025, the wait was finally over. After years of planning, construction, and anticipation, the Vera C Rubin Observatory released its very first test images. Astronomers call this moment first light, the instant a new telescope truly opens its eyes to the universe. And what Rubin saw left the world stunned. The first release was nicknamed the Cosmic Treasure Chest, a vast mosaic built from more than 1,000 exposures. It captured a region in the southern Virgo cluster, the closest large cluster of galaxies to our own, about 55 million light-years away. In a single frame, Rubin revealed 10 million galaxies, spirals, ellipticals, irregulars, each one a city of hundreds of billions of stars, some nearby and detailed, others so distant they appear as tiny specks of light, and all of them together forming a tapestry that feels endless. Zooming in, the detail is breathtaking. Two large spiral galaxies dominate one corner, their arms winding gracefully. Above them, a trio of galaxies mid-collision, threads of material stretching between them. In another region, the scene shifts to what astronomers call cosmic drama. Here, bright stars from our own Milky Way blaze in the foreground. Dozens of galaxies float nearby, clear and distinct, and behind them, a reddish sea of even more distant galaxies fills the background like a cosmic curtain. The image contains more galaxies than any one person could ever count in a lifetime. And yet, this astonishing view represents just 0.05% of Rubin's eventual survey. Another early triumph was the Lagoon Nebula mosaic. This famous star-forming cloud sits just 5,200 light-years from Earth. Through a backyard telescope, it looks like a faint smudge. But Rubin's camera combined hundreds of exposures over just 7 hours to bring its hidden structures into focus. Dust lanes twist across glowing hydrogen clouds. Young stars sparkle like gems within the nebula's heart. The pink and red hues mark regions where new suns are still being born. It is one of the few nebulae visible to the naked eye, yet Rubin revealed it with a richness never seen before. These were just the test images, a preview of what is to come. Over the next decade, Rubin will observe as many as 20 billion galaxies. It will create a cosmic dataset so vast, no single astronomer could study it all in a lifetime. It is nothing less than a new window into the universe. But Rubin isn't just about pretty pictures. Behind the beauty are 4 scientific missions that drive the project forward. The first is the study of dark matter and dark energy. We now know that 95% of the universe is invisible, either in the form of dark matter, which holds galaxies together, or dark energy, which pushes the universe to expand faster and faster. By mapping billions of galaxies, Rubin will trace the cosmic web. It will show where dark matter clumps and how dark energy shapes the expansion of space. This is one of the greatest mysteries in physics, and Rubin may help us uncover answers. The second mission is a census of the solar system. Astronomers expect Rubin to discover millions of new asteroids and comets, some of them small and harmless, others potentially hazardous to Earth. By cataloging their orbits with precision, Rubin could become a vital tool for planetary defense, helping us spot dangerous objects long before they come close. It may also uncover entirely new classes of icy bodies in the outer reaches of the solar system. The third mission is to capture cosmic fireworks. The universe is full of events that happen in the blink of an eye. Stars exploding as supernovae, black holes colliding, sending out ripples in space-time, gamma-ray bursts flashing brighter than whole galaxies, then fading away. Until now, many of these events went unseen because no one was looking at the right spot at the right time. But Rubin's constant sky survey will change that. It will catch thousands of these events in real time, alerting astronomers worldwide within minutes. For the first time, we'll be able to watch the universe's most violent events as they unfold. The fourth mission is mapping the Milky Way. Rubin will chart billions of stars in our own galaxy with incredible accuracy. It will reveal their positions, their motions, and their histories. Together with data from missions like Gaia, Rubin will help build the most detailed 3D model of the Milky Way ever attempted. We'll finally see our home galaxy not just as a blur of stars, but as a living system shaped by billions of years of cosmic evolution. Other surveys have paved the way. Gaia has mapped stellar positions. Pan-STARRS has scanned for asteroids. DAISY has probed dark energy. The Sloan Digital Sky Survey built the first great map of the cosmos, but Rubin will take all of these efforts further, faster, deeper, and on a scale none of them could reach. So when you see Rubin's first images, the cosmic treasure chest, the cosmic drama, the Lagoon Nebula, remember this, they are just the beginning. A glimpse of the power of a machine built not only to see the universe, but to watch it change. From galaxies billions of light years away to the asteroids in our cosmic backyard, Rubin will reveal it all. Not in isolation, not as snapshots frozen in time, but as part of a grand movie, the story of the universe, written in light. The Vera C. Rubin Observatory isn't just changing how we see the universe, it's changing who gets to see it. Unlike many past projects, Rubin's data won't be locked away in private archives. It will be public, open to researchers, open to students, even open to amateur astronomers curious enough to dive in. Anyone, anywhere in the world will be able to explore its vast library of the sky. This openness is revolutionary. For decades, access to cutting-edge astronomy data was limited to a select group of professionals. Now, Rubin is turning the universe into a shared resource, a high-definition record of the cosmos available to all. So what does the future hold? By late 2025, Rubin is expected to enter full science operations, and once it does, the discoveries will begin pouring in. In our own cosmic neighborhood, Rubin may identify hidden asteroids that cross Earth's orbit. Some could be potentially hazardous. Others might become future targets for exploration. Either way, it will transform planetary defense, giving us earlier warnings than ever before. Farther out, Rubin could reveal new dwarf galaxies orbiting the Milky Way. These small, faint galaxies are the building blocks of larger ones. Finding more of them will help astronomers understand how galaxies grow and evolve. On the grandest scale, Rubin will provide new insights into dark energy, the mysterious force driving the accelerated expansion of the universe. By mapping billions of galaxies across time, Rubin will trace the cosmic web with unprecedented accuracy. It may bring us closer to answering one of the biggest questions in science. Why is the universe expanding faster and faster? And then there are the cosmic fireworks. Rubin will catch thousands of supernovae in real time, some within hours of their explosion. These alerts will be shared instantly with astronomers around the world, triggering follow-up observations with other telescopes. For the first time, humanity will be able to watch stellar death and cosmic rebirth as it happens. In just a decade, Rubin will transform our view of the universe, from asteroids in our backyard to galaxies at the edge of time, from the invisible scaffolding of dark matter to the mysterious push of dark energy. It will reveal the cosmos not as a frozen picture, but as a living story, a universe in motion. And perhaps that's the most fitting tribute of all. Vera Rubin once showed us that most of the universe is invisible. Now the observatory bearing her name will show us how that universe changes, night after night, frame by frame, breath by breath. But the real beauty of Rubin isn't just in the discoveries it will make. It's in the way it reminds us that science is a human endeavor, a collaboration across nations, a marriage of technology and imagination, a bridge between the known and the unknown. Every image, every byte of data represents centuries of human curiosity, the desire to look up, to ask questions, to push beyond the horizon. And now, for the first time, the answers won't be kept in dusty journals or behind closed doors. They'll be shared with the world, with you, with me, with anyone willing to look. We stand at the edge of a new era, the era of open, living astronomy, an era where the universe is not just studied by a few, but experienced by all. Rubin will not just watch the sky, it will invite the world to watch with it. We are about to watch the universe come alive, and the story is only just beginning. Thanks for watching.